been through one read of the exam. It's probably going to take till the end of the week, I would guess, to be able to finish it off, perhaps even into next week. Just based on the first initial read, I think you guys did better than you're thinking. So no big worries there. The next topic that we want to begin, we've pretty much polished off thrust fault systems, at least in terms of the basics of how thrust fault systems are going to behave, how we might be able to treat thrust fault systems, and how thrust fault systems can impact the behavior of fluids within an evolving thrust complex. And so the pulse of fluids coming out, the hydrocarbons coming out of the system, and the development of fluid and bases. I think we've talked about that and have a general idea of how that might work. The next topic that we're going to get into is strike-slip, wrench fault systems. What happens when instead of looking at a contractional system, we will start off very, very simple and look at a simple shear system where we're moving in a strike-slip displacement. And how can we begin to understand what's happening in those systems, how various structures develop in those particular systems. After that, the topics that we have remaining for the next few weeks, we need to talk about inversion when we take a fault and reverse the sense of displacement. So start off with a normal fault, change that into a contractional fault. Then from there, we will jump into folds and fold systems, spend a few days trying to understand fold complexes. Then we will jump into a little bit about foliations in systems. How do fabrics develop? What types of fabrics do we see? Lineations, foliations, and then from there into stress and strain. Once we get through here, that will really be a change in the way that we're working and also the way that the topics are going to come towards us. So far, we've been looking at description. What do we see? What geometries do we see? How do we describe these things? How do we classify these things? Then we are going to start trying to understand how might we quantify these things? How might we understand the strain that will result in a particular type of structure? How might we begin interpreting the way that materials behave and how those can control the types of structures that we see in a system? Because ultimately, at the very end of the class, we're going to try to integrate all of our knowledge into a simple concept of stress causes strain. So that's half of structural geology right there. And then the remaining concept is that the behavior of a material will depend on how fast we're trying to deform it. That's the imposed rate of strain versus how fast it can deform by certain mechanisms under certain conditions of pressure and temperature. That's the other half of structural geology. And so those two simple concepts are things we're going to start tying together. So by the time we get to the final, when you take the final, again, you'll probably have 4 or 5 questions on the final total. And they're going to be questions like, okay, we have this material, we have these boundary conditions, here's the pressure, here's the confining. So we have confining pressure, we're going to have temperature, we're going to have the imposed rate of strain. Now, discuss the geologic system that will develop from that. If we did that now, that would be kind of unfair. You would probably respond yes, or maybe you would respond no, but that's it. We're going to build to that. The other thing that we have coming towards us, please remember, field trip is going to be on October 17th. That particular field trip will be a mixture of field mapping, a few stops just to make some observations, and to sharpen our skills a little bit about how do we make observations in the field, how do we begin to recognize structures in the field, how do we collect some field data and come to a conclusion, an interpretation of a particular geologic structure, a particular system. So that trip, we will leave at 7 a.m. on that Saturday, and I will warn well ahead of time, don't be late. We leave at 7 a.m., so if you get here at 7:05, you'll find us gone. Steve?
Where are you meeting to get the ride?
North parking lot.
Just straight that
Yep.
way?
So we're leaving at 7 a.m. We should be back 7 p.m., between 7 and 7:15 p.m. And so you'll need to bring a lunch with you and other things, and I will cover logistics on the field trip before we go. In this particular system, we're also going to talk a little bit about the geology of Oklahoma, because Oklahoma has a rather unique and interesting geologic history. We have a vast array of tectonic provinces. We have an incredible array of structural styles in that particular system. So we're going to spend probably today and probably most of Wednesday on strike-slip fault systems. That's covered chapter 18 in your textbook, and that's a reasonable presentation in the text. If we go back and think about when we began describing faults, we did a strike-slip fault and we drew, again, a stick figure. This is pure physical geology. So if this is our fault, if we have an offset of a system like this, we would term that a, what kind of fault? Right lateral. This would be a right lateral strike-slip fault. If we had a system like this, then we would term it a, oops, I just threw the same system. We would term, again, a right lateral. Yeah, thank you. Okay, so we would term that a left lateral fault system. My brain must still be at home in its box. So I keep it in a box to keep it safe. This would be a left lateral strike-slip fault system. But this is, again, highly inaccurate. What we visualize when we have these sorts of stick diagrams is that we have a single fault plane. That fault plane is vertical in that system. There is no offset vertically. All of our offset is lateral in that particular system. And hopefully after our discussion of thrust fault systems and normal fault systems, we'll realize that that's probably not true. That's probably not 100% of the story. And so what we're going to do is talk about a series of diagrams of how these systems might behave and the types of features we can see associated with strike-slip fault systems. So let's start assuming, and what I'm going to do, aside from flip over this chair, we're going to start here on a series of vertical cross-sections. And so we'll progress upward through the development structures, and then over here with a series of map views in a system, okay? So let's start with a simple cross-section where we have down here, this would be granite basement crystalline material. We're going to put in an imaginary strike-slip fault in the system. We want that strike-slip fault, in this case, to be viewed from above as a right lateral. And so I'm going to put a circle and a plus sign, meaning this is coming toward you. This is going away from you. So if we look from above, that would be a right lateral system. We're going to put some sediments in here. And if I draw my first cross-section, what I'm going to do is just put a dashed line along here. That would be this fault line at depth, okay? So we would be going from, and we can give this an x prime, whatever we want to call it. So this is the fault line at depth. It is not yet visible at the surface. So as we begin to deform, imagine that we're deforming this. This block is coming towards us. This block is going away from us. What happens? Well, we have some intriguing things that begin to happen in this particular system. What we find in the initial phases, as this displaces, is we begin to see some folding in the system, and it begins to propagate upwards. So one of the first things we notice in a system, now this is still at depth, it has not yet gotten to the surface. What we will notice is that we tend to start seeing some folds develop. And we typically label them as just anticlines, realizing that there are likely synclines in between those anticlines. These are unique in that they form an en-echelon pattern. And by en-echelon pattern, remember, when we describe an en-echelon pattern, that means we have some type of a geometric element. So this would be our fold. We take that and we repeat it in a piecewise offset pattern. So this is the entire element right here. So we have it here, we move over, we have it there, we move over, we have it there, we move over, we have it there. That is an en-echelon pattern in that system. So our first piece of evidence that we have an ongoing strike-slip fault system at depth is this type of folding. Okay? Once we begin to have this propagate, so let's put the third one up here. Here is our basement, and we begin to propagate a fault upwards. So we see folding in here, and we finally start seeing a fault moving up towards surface. Now notice, I did not draw this thing stick straight. It is going to curve. What we find is, here is our through-going fault at depth. These folds are going to still be there. And now we start seeing low angle faults developing that have the same sense of displacement. If we happen to draw this correctly, I'm going to take that one, move this over. Now what happens is my fold is going to get offset on this system here, like that. So this is our through-going fault at depth. This is our XX prime. We still have our folds there, and now we're going to start offsetting them on these low-angle faults. This would be termed a synthetic fault. A synthetic fault is a nearly vertical fault that is showing the same sense of offset that we have at depth. So if our fault at depth is a right lateral, then this will be a right lateral fault here. So these are synthetic. That means they have the same sense of displacement as the fault at depth. In your book and in a lot of the literature, these are termed Riedel shears. These were defined actually in 1928 and 1929 in a couple of classic papers, one by Hunskluss and the other by Riedel, looking at small-scale fracture systems and some of the concepts that they were seeing in terms of internal plate deformation. And so sometimes you'll see these referred to as simply R faults. Makes it sound kind of like a pirate. Those are the synthetic faults in that particular system. So our folds, if I can modify this diagram a little bit without guarding higher, then we will have our folds getting offset on these systems. Okay? So in this particular setting, our folds are going to get dissected, they're going to get shifted in this particular system, and this sense of displacement is going to, actually let me modify this so it looks a little bit better for you. Let's go back. Here's X prime. We're going to throw in our low angle faults here. And since they're being offset in a right lateral sense, this thing's going to move this way, this thing will tend to move that way. Okay? They will have a right lateral sense of displacement from here. So we see in this phase here, synthetic faults, low angle. Those faults are going to start at approximately 10 degrees to X prime in that system. These folds are going to start at an angle of approximately 30 degrees to X prime. Now, what we also find is that we begin to form splays on our fault coming up so that it starts to look like a flower or a palm structure. So if we continue, what we're going to do is, let's come to this next diagram here. So now I'm going to have my fault start to propagate up and it begins to splay. I form what is termed a flower structure. In the system that will isolate out these folds in that system, and what we find here, not yet, the main fault still hasn't come to surface. What we find is now we start seeing high angle faults that are connecting up our synthetics. Okay? These higher angle faults are antithetic and are sometimes referred to as R prime, Riedel complexes. So we still have XX prime. The folds are still being offset in the system so that we would have our folds showing the same types of geometries in that system. And if the folds intersect one of these antithetic folds, it'll chop them up again, so we can begin to get a relatively complex fold-fault geometry. A few things to note. In this development, the fault is propagating from basement upwards. So it starts just getting general deformation to the area in a sense of shear. Then it begins to propagate up. We see the first thing to develop are these synthetic faults. These are shear zones, or are faults. They occur at a low angle to the master fault, the through-going fault at depth. Once we get to this stage, we have a well-developed flower structure. It is a relatively narrow zone of deformation. It's not going to be hundreds of kilometers wide. Even though the fault plane itself might be hundreds of kilometers in length at depth, the zone itself may only be 10 to 15 kilometers wide. It's fractional relative to the size or length of the overall fault zone. Does that make sense? Does that, or do we need to go over that again? It's a relatively long, narrow fault zone. So we see initial folding. That means we apparently have a little compression this way. Then we begin to see these developing. These antithetic faults here are going to be at approximately 70 degrees to XX prime as they begin to form. They seem to connect up. The R faults, or the synthetic faults, so the R prime faults appear to be some sort of a transfer or connection with the R faults. And so we're adding on, we're compounding. So we have folding, low angle synthetic faults, higher angle antithetic faults in this particular system as this continues to develop. What happens in the latter stages is we can see this system coming up, develop, begin to bifurcate, but one of these will now become the master fault. That might be on the perimeter, that might be in the central part, but our master through-going fault can finally reach the surface, leaving a zone of folding, faulting on either side. Okay? So that what we would end up with, let's leave that there. In this last stage now, my master fault is there. That's the XX prime fault. I'm going to start seeing a meandering zone of faults that are truncating each other. So I end up with sort of a braided fault system. We give that a fancy term. In structural geology, we call this an anastomosing bifurcating fault system. Okay, so we give it a fancy title. Anastomosing bifurcating fault zone. Yeah.
Okay, you said that the fault is would be like 10 to 20 meters long, and then the actual plane would be much larger.
Hmm?
Did I say that right?
This can be hundreds of kilometers in length, but is relatively narrow.
Okay, so it's narrow.
You don't see this extending for hundreds of kilometers away from the fault. It is really typically less than 15% of the total displacement in width. So we see several things develop. If we go back again, we're starting down here. We're moving this in a right lateral sense. We begin to fold the sediments on top. Then we see the R faults come in, usually at about a 10-degree angle. These are synthetic. They have the same sense of displacement. Then we come in, we start seeing a well-developed flower in the subsurface. Our prime faults come in the system. What we find in this particular case, these are antithetic. That means these would be left lateral. These here are right lateral. These would give you left lateral displacements in that particular system. As we go from this phase into this phase, as they start to braid and connect up, keep in mind, we're going to have folds in here that can get offset and mixed into a series of different blocks. Tim?
Can you describe again why these on the right are right lateral and why those on the left are left lateral?
Okay. If we come back to this, this started off right lateral. As we propagate up, the first main faults that we see, this on echelon pattern right there is synthetic. It shows the same sense of offset. And so if the XX prime is right lateral, then this is going to show right lateral. Okay? These, as they come up, these are transfer faults cutting across our flower to connect up to form a continuum of faulting. So these are going to be left lateral in this sense. These, you can think of those as being small-scale transfer faults. It's just easiest to think of them as antithetic with the opposite sense of displacement. So we have here, since these would be right lateral in displacement, these are going to be left lateral in displacement. What will happen between here and here is that the zone will start to rotate into a narrower fault zone. So we start off with a fault zone here that we can see as some percentage of the total displacement. And here it will begin to rotate down and form a narrower braided fault system. That has folds in it and has the antithetic and synthetic faults starting to rotate in. The synthetic faults will tend to rotate to XX prime. So they will start off at 10 degrees and rotate into 0 degrees relative to the through-going fault. The antithetic faults start off at about 70 degrees to that XX prime, and they will rotate almost to 90 degrees in the system. And our folds will get progressively chopped up into smaller and smaller pieces along this zone, forming a rather intriguing and complex system. Now, as this is going on, we have some other things at play. Strike-slip fault systems can be beautifully complex. When we look at these systems, let's step back a little bit. Can we erase this part? Are we good over here? Because we have some additional things at play. We have to start thinking about how the fault is curving and what can happen at that curvature. And so we want to look at a simple concept. If I have a fault plane, let's say I have a fault plane that curves like that. Okay? So I have a fault It's not stick straight, it's curving a little bit. What happens if this is a system that wants to offset like that, left lateral? Well, if we do that, let's do this. So we have this curvature, right? And this goes up. What happens? We form an opening. We actually have, in this case, what is called a releasing bend. It will tend to open up right in that zone. This will be an area of local extension. And it will start to fill up with sediment. And so that can develop into a region that has localized sedimentation. Into, and I'm going to call it a pull apart. So we would see normal faults, and we would see sediment piling into this local pull apart basin. In the literature, and I think in your text, we use a far uglier word. We call it a rhombochasm. We'll just call it a pull apart basin. That forms in a releasing bend. As we continue to displace, then we can actually stretch these materials out quite a bit. And we can end up with a rather intriguing array of laterally discontinuous sediments in time. If we take our bend the other way, or let's use the same bend and have a separate sense of displacement in there. So we're going to take the same bend, but in this case, this wants to go up, that wants to go down. What's going to happen right there? Well, let's do this. Let's play the handsy fault game. So we're going to come in here. Now this wants to come down. It gets stuck. It's in compression. So we end up here formalizing or forming a series of thrust faults. So we see local thrust faults here in a zone of compression. This is called a restraining bend. In this particular case. So now we have thrust faults and uplift, but it forms a Y. And so if we were to draw a cross section of this, what we would see is these different thrust faults coming out from a central fault plane. And these would tend to propagate up toward the surface, but they would be concentrated locally. So that we would make basically a pile here, an uplift with thrust faults and compression within the strike slip fault system. This would tend to localize quite a bit of earthquake activity. When we think about recent strike slip fault systems that have caused damage, if you go back, if you think about the earthquake that occurred in Haiti, just south of Port-au-Prince, that was in a slightly compressional zone on that system. And in that particular earthquake, over 230,000 people perished. At a magnitude 7.5 earthquake. If we think about a recent earthquake in New Zealand near Christchurch, it was a fairly, we would call it a minor earthquake. It was not, it was in the sevens, and it caused billions of dollars of damage because it was in a compressional zone and we had intense shaking right here in this system. If we go to California, we look at the Los Angeles area. What are some of the odd characteristics of Los Angeles other than the fact that it's Los Angeles?
Valleys?
Hmm?
Valleys?
You have valleys, you have a very large oil field in that system, and what happens is you have, for the most part, a pull-apart basin in the greater Los Angeles area, but as you go north, the fault bends the other way, and you have the hills north. And that gets into a compressional zone. The most recent earthquake there caused billions of dollars worth of damage, and that was in the restraining band of that particular system. So add on to this the fact that we can develop localized releasing bins, localized restraining bins, and we end up with somewhat of an intriguing mishmash of structures. In a strike-slip fault system, we can see all of the above styles of deformation. We can see normal faulting in our releasing bend. We can see compression in our restraining bend in the system. We can see folds that have been offset in different ways. We can see faults that have the same sense and the opposite sense of distortion in that particular system. And once we start shifting, we can move different rock types next to one another. And so that description gives us what is, if you celebrate obtuse language and technical jargon, that gives us the formal definition of a strike-slip fault zone. So a strike-slip fault zone is a fault zone that shows the following: lateral juxtaposition of dissimilar lithologies. Along an anastomosing bifurcating fault system. That's the formal definition of a strike-slip fault. Blech. That's my favorite sentence in structural geology. Yes. Lateral juxtaposition of dissimilar lithologies along an anastomosing bifurcating fault system. Messed up. And we see all senses of deformation in this characteristic system. Some of the key characteristics that we want to keep track of is that your synthetic faults start off at a low angle to the through-going fault plane and tend to rotate toward it. The antithetic faults tend to rotate toward 90 degrees to that through-going fault and are shorter and tend to connect up blocks. Your folds get truncated in multiple horizons and you end up with an intriguing arrangement of folds that are plunging in different directions, and they're a little bit difficult to connect back up sometimes. We can have restraining bends, we can have releasing bends in that particular system. So this would be a strike-slip fault in a continental area where we're propagating the fault zone from basement upward through a sedimentary basin. Now, classic strike-slip fault systems in the world will include things like the San Andreas. That's one of the great classic strike-slip fault systems in the world. About 600 kilometers of net offset on that particular strike-slip fault system. But we see releasing bends, we see restraining bends, we see all of these different characteristics along the San Andreas. The Alpine fault system in New Zealand is a classic strike-slip geometry fault. The Anatolian, particularly the northern Anatolian fault that cuts through Turkey, is a classic strike-slip fault system. If we think about earthquakes and the magnitude and number of fatalities, strike-slip fault systems seem to be the most dangerous, seem to have a greater portion of fatalities in an earthquake related to these strike-slip fault systems. And so classic systems, and we want to begin to investigate these, would be San Andreas, the Alpine, that's in New Zealand, the Anatolian system that cuts through Turkey. The most recent big earthquake in the Anatolian system was near Izmit. In that system, roughly 30,000 people perished in that particular earthquake. If we look, this one, the Taishan, is in China and is likely the most dangerous strike-slip fault system in the world. Portions of the Taishan slipped in 1976. It was a fairly large magnitude quake, up in the 8s. The official death toll from Chinese government agencies was around 275,000 perished. Relief agencies that went into the city afterward for search, rescue, recovery estimate that it was actually closer to 750,000 people perished. That particular situation, the city was built on top of a mine complex, and in the quake, the mines collapsed, the city collapsed into the mines, and then everything was buried. So they were never able to recover everyone. The Taishan, if you go further towards the west in China, the biggest earthquake ever recorded was, or the greatest number of fatalities on record, if you look at the record, it says 830,000. And then there's a little asterisk that we were unable to count more. We quit counting. And so we don't know what that upper limit was in that particular system. And we want to ask ourselves, how are these behaving? What sorts of tectonics, what sorts of things do we have going on as we begin to think about these faults? And so we need to review a little bit of physical geology again and bring up a term. In your textbook they use transcurrent. I prefer transform. Do you remember how transform fault works? A transform fault is a type of strike-slip fault that connects active tectonic elements. So let's take a look. So we're going to start off with a simple spreading system, mid-ocean ridge. Do you remember how mid-ocean ridges work? So let's go in, let's put in a mid-ocean ridge here. That's a mid-ocean ridge. We're forming new oceanic crust here, so if we were to put a cross-section, what we would tend to see is this type of a scenario, and we would have eruptions of basalt coming up in this area. So this will be basalt, and it's forming new crust here. So this is moving this way, that is moving that way. It is spreading apart. And it can be spreading apart slowly, just a few centimeters. It can be spreading apart relatively fast, up to 10 centimeters per year. What we find is that a lot of times the mid-ocean ridges are not continuous. We have relatively short segments, and then we have a little transfer fault. So we find a scenario like this, mid-ocean ridge. Here we have something intriguing. If we look at this, that's moving that way, this is moving this way, that's moving that way, that's moving that way. If we just look at the geometry, you would be very tempted to say this is the left lateral system. But it's not. This is a transform. Let's come down to here. That's moving that way, that's moving that way. This is moving this way, that's moving that way. So in between, in this area here, we actually see right lateral displacements. If we were to draw this area, that's what we measure. Okay? If we were to go out here, we don't see any strike slip deformation. Because they're both moving the same direction. When we go here, we don't see any strike slip deformation because they're both going the same direction. What we do see is if we go back and look at this, if we exaggerate a little bit, our seafloor topography is highest at the mid-ocean ridge. So I'm going to superimpose a second ridge down here. So we're seeing this one and we're seeing this one. What we see in this area here is normal faulting. One side's higher than the other. And then as we move away, that offset goes to 0. In tectonics, this region in here is just termed a fracture zone. This is our transform. So we have fracture zone and transform fault in that system. We see the same geometries, whether we are offsetting two mid-ocean ridges two subduction zones or a subduction zone and a mid-ocean ridge. Same basic types of geometry for a transform fault system. So if we go back and look here, remember when we were talking about strike slip faults, we were assuming it's propagating up through a sedimentary basin, and we were assuming that it was inside of a plate, not an actual plate boundary. Well, we have a little bit of added complexity that we need to talk about next time, because when I look at this, that is a transform fault, a big one. That's a transform fault. This one, yeah, we got to think about this one. This is an intriguing little monster. We have to think about this one. This is a very intriguing system. These two are going to turn out to be escape features. So, transform, transform, escape, escape. The number of worldwide faults that we can truly say fits our original definition of a strike slip is actually limited in that system. And so we'll try to understand these a little bit next time. All right.
And San Andreas being mentioned, AAPG is having a Shisky movie night on Thursday. Here at 6:30.
The magnitude 12?
We're actually watching San Andreas, that movie, so.
That's a great
We're
movie.
gonna, I don't know how awful it is, and there's gonna be free food and stuff, so you'll be getting an email today.
It's horrible geology, but it's a great movie.
Yes, that's
It's-
what we were thinking.